Now we're going to move on to a reduction table. We've looked conceptually at why redox reactions occur. Now we need to look at how they're organized into a table and given values for that potential to be reduced. So this is a table of standard reduction potentials. It's given in terms of half reactions. The half reactions are all organized as reductions. So that's why it's called reduction potential. And we have the potential given here for the volts that are produced when compared to hydrogen. So we'll talk about that in a moment. There's a standard hydrogen electrode that we can set to 0 and compare everything else to whether it's better at getting oxidized or reduced and what those potentials are. All right, so again, these are reductions. So at the top, we have positive numbers for things that are very good at being reduced. They like to be reduced. A potential is produced when these substances are reduced. So we have our half reaction organized with the oxidized form. It gains electrons and produces the reduced form. So in terms of a metal, we're going to start with the ion, gain some electrons, and produce the metal. But we have other substances that can get reduced as well. So for example, fluorine, you can relate it to, fluorine is very electronegative. It likes to get electrons. So it is very easy to reduce fluorine to a fluorine ion, a negative fluorine ion. And you see it has a high potential there. All right, so the potential is its ability to get reduced. So down at the bottom of the table, you see negative numbers. These are things that do not work well at being reduced. So a lithium ion, for example, does not like to gain electrons to form lithium. And if you remember the demos with sodium and lithium and potassium being thrown into water, they are very reactive. Those metals want to lose electrons and form the ions, and those ions are very stable. So if you try to go in reverse and put electrons on those ions, it's not going to work very well, and therefore these have negative potentials for reduction. All right, so the potential, the E0, is written as reduction. So these reactions are all as written. They're written as reduction, and those are potentials as they are written. The more positive the potential, the greater its tendency to get reduced. It likes to get reduced. The substance on the reactant side is the substance that likes to get reduced. These reactions are reversible. That's how we are going to get our redox reactions. These are all reductions, but if you appropriately pair it up with something that would prefer to get oxidized, then you can get a redox reaction. Something that's important to note is that to balance chemical equations, you're going to have to use coefficients, but those coefficients do not change the potential. The electrons, the orbitals are still the same energy apart, so it's still the same potential that is being produced. So the stoichiometric coefficients do not dictate your potentials. All right, so let's look at how this table is organized. There's lots of different ways to organize the table. Sometimes they're in alphabetical order. Sometimes they are starting with the negative first and moving towards the positive. But the most standard form of the table is to organize it according to hydrogen and move the positive potentials above it and the negative potentials below it, just like a number line. So we are going to use that format of the table. And if you do it that way, the stuff up here in the top left corner are substances that are easily reduced. So these are written as reduction. We have positive numbers, very high positive numbers. So the higher it is on the left-hand side of this table, these are substances that are easily reduced. So if they get reduced, that means they are strong oxidizing agents. So fluorine gas is not something I have ever worked with. And I probably would not want to work with it. And if you have fluorine gas that you have to work with, you probably have a lot of safety precautions you have to follow because it's a very strong oxidizing agent and it is willing to take electrons from things sitting around it. So remember, it's easily reduced, so it's a strong oxidizing agent. So things down here that are on the product side, remember, these ions, they do not like to be reduced. They have negative potentials. But if you look at the other side of the reaction, those metals in their metallic form, their elemental form, their neutral form, they are easily oxidized. So if it's hard to reduce the ion, that means that product is very easy to oxidize. So these are strong reducing agents. So if you put things together that are on opposite sides in this diagonal, so top left with bottom right, you can get a redox reaction, a spontaneous redox reaction. So just remember, it's if something above it on the left with something below on the right, you will get a spontaneous reaction, even if they're close together. So if you can kind of look real closely here, you see nickel 2+ here and cobalt solid here. There would be a spontaneous reaction there because nickel 2+ favors getting reduced more than cobalt 2+, but the cobalt would be a little bit more reactive. So we get this diagonal here, and that shows you where the reaction. Now, if we put these two substances together, the other part of the reaction is the products. So let's go ahead and just write this out. So if I put nickel 2+ with cobalt solid, they will spontaneously react and they will produce nickel solid and cobalt 2+. All right, so let's talk a little bit more about the standard hydrogen electrode. Electrodes can often be just pieces of metal, like if you have the copper and the tin that we had in the demo earlier, you can stick those in, hook some wires to them, and they would make great electrodes. But not everything is a solid or an easily manageable solid. So if you have something like hydrogen gas, an H+ that you're trying to use as an electrode, you have to set it up in a special way. So we have this special glass tube where we can pump in hydrogen gas. We're using platinum metal because it's very inert, not very reactive. And we can bubble in the gas and we can have it in a HCl solution, which is a provider of H+. And we can have the reaction at the surface of that platinum electrode. And remember, on our redox table that we just covered, everything was compared to hydrogen. So this is the standard hydrogen electrode, also called She, and that's what everything is compared to. And for it to be standard, we need 1 molar concentrations and 1 atmosphere of pressure. So this is how we get our table of reduction potentials. All right, so conceptual example, looking at the table. I want to look at chlorine gas, cobalt metal, and nickel 2+ aqueous. And I want to know which one's going to be the best oxidizing agent, reducing agent, and similar questions that we had with the orbitals. Now we're going to use the table. All right, so I've pulled a piece of the table, hopefully we can see, and I am highlighting the chlorine gas, nickel 2+, and cobalt on the screen. So which would be the best oxidizing agent? So oxidizing agents get reduced. So this is a table of reduction. The things that like to get reduced are at the top of the table. So Chlorine is on the reactant side and it's towards the top. And these other two things, cobalt does not like to get reduced. And nickel's lower than the chlorine. So the top left corner or something above and to the left is the best at getting reduced. So it's the best oxidizing agent is going to be the chlorine. Chlorine gas. So the best reducing agent would therefore be down here at the bottom right. So best at oxidizing, best at getting oxidized. So it's the reducing agent, the best reducing agent. So understanding your table and how it's set up is key to helping you understand some of the conceptual questions. So cobalt would be the best reducing agent. Is chlorine capable of oxidizing CO? So, well, let's first look at chlorine and CO. Well, I get a spontaneous reaction there because I have something above and to the left combined with something below and to the right to get that diagonal. It's a spontaneous reaction. But is it oxidizing the cobalt? So my cobalt is going to react and produce cobalt 2+. That is oxidation. So the chlorine is oxidizing the CO. So that answer is yes. All right, is nickel 2+ capable of reducing cobalt? So now we're going to look at nickel 2+, and can it reduce the cobalt? Well, I get a spontaneous reaction here. So that's good to know. Nickel 2+ reacted with cobalt will produce the nickel solid and the cobalt 2+. So I've written that reaction on the screen right here. But the question is asking, can it reduce the cobalt? The cobalt is getting oxidized. So nickel is not capable of providing electrons to cobalt, and cobalt is not very good at accepting electrons because that would give the metal a negative charge. So it's spontaneous, but it's not getting reduced. So the answer here is no. So there's no reaction on the reduction table where cobalt could actually get reduced.